Currently, your vehicle's engine might appear to operate perfectly normal, yet a single contaminated sensor could be secretly robbing horsepower, raising fuel bills, and accelerating engine deterioration without ever illuminating a dashboard warning indicator. This hidden threat makes the situation particularly treacherous. How does a device smaller than your thumb cause a vehicle to feel underpowered, waste gasoline, and flunk emissions inspections simultaneously? Service centers and repair facilities throughout America witness an identical scenario repeatedly. Ignition components get changed, coil packs are installed, fuel delivery systems are questioned, and enormous sums vanish. The underlying issue persists until someone eventually addresses a sensor that rarely receives attention. And surprisingly, it's not the component most mechanics initially consider. There exists an overlooked troublemaker that gradually collects contamination over extended periods, transmits corrupted information to the engine control module, and transforms a completely functional power plant into a persistent underachiever. During this presentation, we'll examine the most troublesome engine monitoring devices individually. However, the component that malfunctions most frequently, the one virtually never serviced, and the one capable of dramatically altering your engine's performance within moments, won't be disclosed until the conclusion. Number 13. The MAF sensor, mass airflow. The mass airflow sensor stands as one of the most vital, yet simultaneously most overlooked elements in contemporary fuel injection power plants. Its function involves measuring with remarkable accuracy every single gram of atmospheric air entering the combustion chamber. Most MAF units installed in American market automobiles employ a heated wire configuration utilizing an extraordinarily fine platinum filament, approximately matching human hair thickness. This filament receives electrical heating to maintain constant temperature, and when intake airflow passes across it, the cooling effect directly correlates with airflow velocity. What the engine control unit actually monitors is the electrical current volume necessary to maintain that filament at steady temperature. That current measurement instantly converts into air mass information refreshed within milliseconds. The significant issue emerges when microscopic particulate matter, oil vapors from aftermarket performance filters, or general atmospheric pollutants cover that fragile filament. Once contamination occurs, its heat transfer characteristics alter, and the information transmitted to the vehicle's computer becomes unreliable. The engine control unit now calculates incorrect air volume entering the power plant compared to actual conditions and compensates by supplying improper fuel quantities. The resulting symptoms frequently confuse diagnosis: significant horsepower reduction during aggressive throttle application, fuel mileage, deteriorating without apparent cause, erratic engine speed at standstill that appears intermittently, and in advanced situations, the power plant dying when decelerating to a halt. Service data from American automotive facilities indicates that approximately 40% of automobiles experiencing improper mixture diagnostic codes contain contaminated MAF sensors, not defective units. Correct maintenance demands specialized MAF cleaning solution and a contactless technique that never physically contacts the measurement component. However, another air calculation sensor operates on a completely different mechanism. Number 12, the MAPI sensor manifold absolute pressure. The manifold absolute pressure sensor represents an alternate approach for determining engine workload. Frequently employed in speed-density fuel management configurations, present in numerous domestic vehicles. Rather than measuring airflow quantity directly, the MAP sensor gauges the pressure level within the intake runner. It employs a piezoresistive component that alters electrical resistance, responding to pressure exerted against its membrane. In basic explanation, it transforms engine demand into an electrical output. When the throttle valve remains shut and the power plant idles, intake vacuum registers high, and the sensor indicates reduced absolute pressure measurements, characteristically between 20 and 30 kilopascals. During maximum throttle acceleration, vacuum decreases and pressure climbs toward atmospheric levels, approximately 100 kilopascals at ocean elevation. The engine control unit merges this information with crankshaft rotation speed and incoming air temperature to determine entering air mass through sophisticated thermodynamic calculations. The essential breakdown point typically isn't the monitoring device itself, but the vacuum connection supplying it. Damaged vacuum tubes, inadequate connections, or somewhat detached lines permit leakage that thoroughly corrupts pressure measurements. The sensor indicates reduced vacuum than actual, causing the engine control unit to assume the power plant experiences greater demand than reality. The consequence is surplus fuel delivery, astronomical fuel expenditure, dark exhaust emissions, and continuous rich fuel fault indicators. In practical workshop analysis, merely cleaning the MAP sensor opening and confirming tube condition resolves approximately 80% of problems attributed to the sensor. However, there exists an even more powerful sensor regarding emissions management. Number 11. The oxygen sensor, also known as the lambda sensor. Oxygen sensors positioned in the exhaust pathway serve as the engine computer's monitoring equipment for tracking combustion effectiveness continuously. They perpetually adjust the air-fuel balance thousands of iterations every 60 seconds. Most American automobiles utilize zirconia oxygen sensors, which depend on a ceramic component heated beyond 300 degrees Celsius. This component produces a voltage determined by the variance in oxygen levels between combustion gases and ambient atmosphere. When a power plant operates at the perfect stoichiometric proportion of 14.7 portions air to 1 portion petroleum, the sensor generates roughly 0.45 volts. If the balance becomes lean and oxygen presence in the exhaust rises, voltage decreases beneath 0.3 volts, indicating the engine control unit to increase fuel. With rich balances, voltage climbs beyond 0.6 volts. The primary difficulty develops when these sensors accumulate contamination from lead, silicone, silicylcyanine, or phosphorus buildup, frequently resulting from inferior fuel or lubricant combustion caused by deteriorated compression rings or stem seals. These contaminants chemically damage the zirconia component, reducing its reaction speed and diminishing accuracy. The sensor continues functioning, but lethargically, transmitting postponed signals that the engine control unit finds difficult to process accurately. The outcome is gradual fluctuation between rich and lean balances, elevated fuel usage, observable horsepower decrease, and virtually certain failure during pollution inspections. Nevertheless, there remains one location sensor whose breakdown generates a fundamentally different symptom collection, and that's where this narrative becomes increasingly compelling. Number 10. The TPS throttle position sensor. The throttle position sensor is a precision variable resistor attached directly to the throttle pivot, and its responsibility involves informing the engine computer precisely how much throttle the operator requests at every individual instant. Despite its simple appearance, it's a vital element. Within the sensor, there exists a circular resistance pathway, and a sliding contact travels along that pathway as the throttle valve opens and shuts. This separates the reference voltage proportionally to throttle angle, characteristically generating approximately 0.5 volts with a throttle completely shut and approaching 4.5 volts at maximum throttle opening. What the engine control unit accomplishes with this data is fundamentally essential. It determines whether the operator is moderately accelerating, where fuel conservation is paramount, or applying maximum throttle, where the power plant requires enriched fuel balances and aggressive spark advance for peak horsepower. The genuine difficulty starts when the internal resistance pathway begins deteriorating or accumulates contamination, generating inactive zones. In those areas, the voltage output momentarily disappears or varies unpredictably. These inactive zones nearly always emerge at the most regularly employed throttle locations, like consistent interstate cruising or increased standstill in congested conditions. From the operator's perspective, this manifests as erratic acceleration, abrupt hesitation, momentary horsepower reduction at particular pedal locations, or in severe situations, total power plant shutdown when the throttle traverses through those deteriorated sections. In expert analysis, mechanics confirm TPS condition by gradually opening the throttle while observing real-time voltage information on a diagnostic instrument, searching for abrupt decreases or increases that distinctly reveal internal deterioration of the variable resistor. Number 9, the crankshaft position sensor. Without the crankshaft position sensor, a contemporary power plant is essentially sightless. This compact sensor positioned extremely near the flywheel or a serrated reluctor ring on the crankshaft produces flawlessly synchronized electrical impulses each time the projections pass its electromagnetic tip. What's genuinely occurring is that the engine control unit employs these impulses to understand the precise location of every piston constantly and the exact velocity at which the power plant rotates. This data is what enables the computer to establish precisely when to deliver fuel and when to trigger the ignition. When this sensor accumulates contamination from metallic particles, carbonized lubricant deposits, or general filth, the output becomes corrupted and sporadic malfunctions start manifesting. The power plant may shut down when warmed without notification, require extended cranking before ignition, or lose ignition for millisecond intervals while operating. In American service facilities, it's remarkably frequent to observe power plants that seem to possess serious ignition or fuel delivery difficulties completely restore after nothing beyond cleaning the sensor tip, extracting metal fragments with a pristine cloth, and applying electrical connection cleaner. However, understanding crankshaft location alone proves insufficient. The computer additionally requires understanding precisely what the camshaft is executing. Number 8, the CMP camshaft position sensor. The camshaft position sensor operates together with the crankshaft sensor like two flawlessly coordinated timepieces. While the crank sensor informs the engine control unit overall power plant velocity and location, the camshaft sensor discloses the precise phase of the combustion sequence for each cylinder. This permits accurate sequential fuel delivery and precise management of adjustable valve timing mechanisms. The sensor typically mounts in the timing housing or directly on the cylinder assembly, reading a trigger disc or a singular metal extension on the camshaft. Its genuine responsibility is transmitting one distinct reference output per camshaft rotation, identifying cylinder number 1 at its power stroke. When this sensor begins deteriorating from lubricant contamination, heavy sludge, or internal fracturing, the engine control unit loses that precise reference and transitions into a compromised mode. Sequential delivery is replaced with batch delivery. Standstill quality becomes unpredictable, and cold ignitions require substantially longer. Numerous power plants develop slight hesitation between 2,000 and 3,000 revolutions per minute that becomes mistakenly attributed to ignition coils or fuel injectors, when truthfully a contaminated camshaft sensor is transmitting weak or corrupted outputs. A straightforward visual examination and cleaning of the sensor's monitoring surface can substantially restore seamless performance. However, there exist sensors that are considerably more disregarded, and they accumulate dirt simply by atmosphere flowing across them. Number 7, the IAT intake air temperature sensor. The intake air temperature sensor is typically a minuscule element installed into the intake runner or incorporated into the air intake channel, so inconspicuous that most operators don't even realize it exists. Its responsibility sounds elementary, gauging how warm or cool the atmosphere entering the power plant is. However, what's genuinely occurring is essential for fuel management. Cool atmosphere is denser and holds more oxygen per unit capacity, while warm atmosphere is less dense. The engine control unit applies this sensor's information to precisely adjust how much fuel to deliver on every combustion sequence. Over duration, the sensor becomes covered with lubricant vapor, adhesive particulates, or buildup from oiled air filtration. Once contaminated, the internal thermistor can no longer precisely detect the genuine temperature of the incoming airflow. The consequence is a measurement that's artificially warmer or cooler than reality, forcing the power plant to operate somewhat rich or somewhat lean constantly. This produces a subtle but persistent reduction of horsepower, elevated fuel expenditure, and in certain situations, mild detonation in extremely warm environments. Mechanics regularly discover that thorough cleaning with electronic cleaner without contacting the delicate component restores rapid sensor reaction and stabilizes the air-fuel balance. However, there exists another temperature sensor that manages something even more essential: the temperature of the power plant's own core. Number 6. The engine coolant temperature sensor. The coolant temperature sensor is one of the most powerful sensors in the complete engine control configuration. Despite being infrequently suspected, it informs the engine control unit how cold or warm the power plant itself genuinely is. And the computer establishes numerous essential determinations on this singular input. During cold ignitions, the engine control unit enriches the balance, raises standstill velocity, and modifies spark advance determined by coolant temperature. As the power plant warms, those approaches progressively diminish. When this sensor becomes covered internally with oxidation, mineral deposits, or sludge from aged coolant, it starts reporting inaccurate temperature information. The engine control unit may assume the power plant remains cold when it's completely warm, or already warm when it's actually cold. The consequence is surplus fuel expenditure, harsh standstill, difficult cold ignitions, cooling mechanisms operating at inappropriate intervals, and extended power plant deterioration caused by incorrect fueling. Numerous power plants that appear to possess complicated performance problems are restored to flawless operation after replacing or cleaning a defective coolant temperature sensor. And yet, there remains one sensor remaining that virtually nobody ever cleans, despite it quietly creating some of the most costly difficulties of all. Number 5. The vehicle speed sensor, VSS. When the velocity indicator needle begins fluctuating erratically, the gearbox starts making unusual shift choices, or the cruise management randomly deactivates itself. The silent perpetrator is frequently the vehicle speed sensor. This sensor is typically positioned on the gearbox casing or the differential assembly, and it produces electrical impulses proportional to the actual rotational velocity of the wheels or the gearbox output component. What's genuinely occurring is that each of those impulses is transformed into information the engine control unit employs to understand how rapidly the automobile is traveling, when to upshift or downshift, how to control fuel interruption during deceleration, and when to engage mechanisms like cruise management and grip logic. When the sensor accumulates contamination from lubricant, pavement grime, metallic particles, or sludge, its output becomes corrupted. Impulses arrive incomplete or irregular, and the computer may assume the automobile is traveling faster, slower, or even totally stationary while it's still moving. In practical analysis, mechanics regularly discover that merely cleaning the vehicle speed sensors, extracting metal fragments adhered to its electromagnetic tip, and flushing the connector with electrical connection cleaner restores a steady output and removes irregular shifting that numerous operators confuse for serious gearbox breakdown. However, there exists an even more vital sensor, one that monitors the interior of the power plant, like a sophisticated acoustic device. Number 4. The knock sensor. Fastened directly into the power plant block is what is fundamentally an acoustic device that perpetually monitors every combustion occurrence inside the cylinders. This is the knock sensor engineered to identify particular vibration wavelengths, generated by irregular combustion or detonation. What's genuinely occurring is that this piezoelectric sensor transforms mechanical oscillations into electrical outputs that the engine control unit examines continuously to establish whether the power plant is starting to knock from reduced octane petroleum, surplus heat, or excessively aggressive spark advance. When knock is identified, the engine control unit responds within milliseconds, delaying spark advance and somewhat enriching the balance to safeguard the power plant. The difficulty starts when the sensor accumulates covering from contamination, oxidation, hardened lubricant, or is mounted with improper torque. Its accuracy decreases, and it no longer precisely conveys those vital vibration characteristics. The result is hazardous in dual ways. Either genuine detonation remains unidentified, and the power plant functions on the threshold of destruction, or misleading outputs compel the engine control unit to perpetually reduce advance, stealing horsepower and making the automobile feel heavy and lethargic. Merely cleaning the attachment surface and connector and reinstalling the sensor with correct torque frequently thoroughly transforms power plants that feel deteriorated or underpowered. However, there exist sensors that don't safeguard the power plant. They alert you only when it's nearly too delayed. Number 3, the oil pressure sensor. The red lubricant pressure notification indicator on the instrument panel is one of the most dreaded warnings for any operator. And behind that indicator is typically a compact pressure sensor that receives minimal consideration until something malfunctions. This sensor is installed into a lubricant passage in the power plant block or cylinder assembly, and its function is elementary, but vital. Identify when lubricant pressure descends beneath a secure limit. Internally, a membrane or pressure responsive component deforms under lubricant pressure, activating or deactivating an electrical pathway or producing a proportional output in more sophisticated configurations. Over duration, the sensor's inlet pathways can become blocked with sludge, varnish from carbonized lubricant, or particles, creating a blockage that stops genuine lubricant pressure from accessing the measurement component. In that circumstance, the power plant may be operating with dangerously reduced lubricant pressure while the sensor indicates normal measurements, or the reverse, activating misleading notifications from sluggish and irregular reaction. Facilities have recorded power plants displaying perfect pressure on the instrument panel, while an external mechanical instrument discloses critically reduced measurements. That's why cleaning or replacing the sensor during significant services can be the distinction between a safeguarded power plant and one advancing toward devastating breakdown. However, there's another seemingly innocent gauge that deceives more frequently than most operators understand. Number 2, the fuel level sensor. The fuel indicator feels like a secondary consideration until the moment your automobile stalls on the interstate while still displaying a quarter reservoir. Behind that deceptive needle is the fuel level transmitter, a sensor that exists submerged inside the fuel reservoir and is virtually never cleaned or examined over the complete existence of the automobile. This configuration employs a mechanical buoyancy device attached to an arm that slides across a variable resistor, altering electrical resistance as fuel level climbs and descends. What's genuinely occurring is that the instrument cluster or engine control unit transforms that resistance into the fuel level indication you observe. Over the years, the resistive connections oxidize, varnish from inferior petroleum accumulates, and contamination deposits generate misleading inactive zones. The consequence is indicators that fluctuate erratically, become frozen at half reservoir, or react extremely gradually after refueling. In specialized facilities, these assemblies are extracted. The resistive pathways and connections are thoroughly cleaned with appropriate cleaner, and buoyancy movement is verified for seamless performance. Numerous complaints about surplus fuel expenditure actually originate with the deceptive fuel level sensor. However, none of these sensors matter if the communication network that links them is malfunctioning. Number 1, sensor connectors, and wiring harnesses. In innumerable sophisticated diagnostics, hundreds of dollars are invested replacing sensors that seem defective when the genuine perpetrator isn't the sensor whatsoever, but the connectors and wiring harness powering it. Every sensor relies on three fundamental requirements: accurate power delivery, solid grounding, and a pristine output pathway back to the engine control unit. What's genuinely occurring in millions of aging automobiles across America is that oscillation, humidity, power plant heat, and minor collisions gradually compromise wiring, pins, and connections. Green oxidation develops inside connectors. Sporadic contact emerges. Conductors fracture internally beneath intact insulation, and grounds detach and reconnect with every irregularity in the pavement. Diagnostic instruments display malfunction codes indicating temperature sensors, oxygen sensors, location sensors, or pressure sensors. However, in the facility, mechanics observe that merely manipulating the harness causes the difficulty to manifest and vanish. What most operators never witness is that a comprehensive cleaning of connectors with dielectric cleaner, correcting grounding locations, repairing inadequate splices, and appropriately securing the harness can remove electronic phantom malfunctions completely. That's why seasoned mechanics always examine wiring and connectors before replacing a costly sensor. Because frequently, the difficulty isn't the element itself, but the channel that transports its data.